Hi everyone. With Citus, with this release of Citus, we really put the focus on the ease of scaling out. So regardless, if you start from a single basic tire cluster, which means one coordinator node and no workers, we want to be absolutely sure that you will be able to quickly scale out without any pain points, even if you made some bad decisions or forget to do some things at the beginning of your journey with CosmosDB for PostgreSQL. So let's start with a simple table, observations, which already apparently was created by me beforehand. So let's drop it and create it again, just so we make sure I don't have any leftovers from me trying this before. So we have this simple table observations that we'll fill with some data. It's just several fields, tenant ID, measurement, payload, observation time. And we want to put some data in it, but where to get data? And one of the things that we want to ease is not only scaling out, but getting your data into the cloud. So a common pattern of getting data into the cloud is to use a service like Azure Blob Storage to use it as a staging environment or as a target environment for your, for example, IoT devices to write data to, and then directly pull it into your Citus cluster. So we enabled an extension in Citus, which is called Azure Storage. We can see it's already installed in this case. We can see it here. And we can use this extension to operate on existing blob storage containers. And I prepared the container beforehand, which is named PG-ABS, which is PG for Postgres, ABS for Azure Blob Storage. And it's a public container. Public is just the container name. Its accessibility level is set to container public because this allows me to access its content without adding any access keys, though you can also do that if you have a private container. So we will use the blob list function from the extension to show every file in this public container, how much space it how much storage it uses, and its MD5 checksum. So calling this, we see that this container has several files. We will be pulling in observations one CSV GZ, which is a comma-separated values file with zip compression. And it weighs in around 11 megabytes of data. So let's pull that in using the copy command. And you can't do this on normal PostgreSQL without the Azure Storage extension. You can install the extension and do it. But with our extension, the database recognizes blob storage URLs and is able to do API SDK calls to obtain the data and directly pull it into your database. So the moment we execute this command, a connection is made to Azure Blob Storage. The data is fetched over the network between the services, decompressed, and ingested into the table itself, so that you didn't have to copy it anywhere beforehand. You just directly ingest it from the blob storage. And you can see that we loaded 3 million records into the observations table. We can quickly show that. We have all the data inside. We can just show some records of it. And we have some random data, or pseudo-random data. And now we can also check the Citus tables. Citus tables shows you the actual distributed tables that the system knows about. And we don't have any. And one of the frequent beginner mistakes, or perhaps not even a mistake if you started in the basic tier and didn't think that you will need to distribute this table because it started out small and you didn't anticipate it. But then you suddenly realize that, hey, I need to distribute this table because I want to scale it out. It needs much more data than I anticipated. So in the past, if you forgot to do that and had a lot of data in the table and tried to distribute your table, then you would end up with a blocking operation. So this call would be blocking. And let's show it. I will open a second connection to the same cluster where I will try to insert some data into the table while I am writing to it. And as you can see, the insert on the right hand is blocked and waiting for the operation on the left connection to finish, and only after it's finished, I'm done. And this means that your application essentially is not performing writes, which might be very problematic from the business perspective. So in Citus 11.11, we introduced a new functionality called create distributed table concurrently. So I will drop the observations table again. Let's close this connection to see some more. Let's recreate our table the same way as we did before. And I will load the data slightly differently this time around, just to show you another API function from the Blob Storage extension. So here we are doing an insert into select from Blob Storage blob get, which allows me to fetch a single file. And as you can imagine, this allows us to do some more on-the-fly manipulations of the data. For example, if I wanted to, I could change or cast some field on the fly. And we are just showing it to show you the flexibility in the method. Okay, now we will do the same thing. We will distribute the table, but we will do it concurrently. Let's get some space here and connect to the cluster again and prepare our insert operation. So now I will first show you that this table is indeed has some data in it. So that's the 3 million rows that we saw beforehand. And we use the same thing. So create distributed table concurrently, the name of the table, and the column that we want to distribute on. So in Citus, you have to tell the database what's your distribution column. The value of this column will be then used to decide where the data based on the value goes to which chart and on which node. So I'm going to execute this now. And while this is being done, I'm inserting rows in the second terminal. And you can see the operation on the left is still ongoing, while your application can perform insert statements into the table and other modifications. And this essentially means that this is a safer operation that can be done online without a lot of disruption in your business. So let's close this. Now the table is distributed. We can see that there are more rows inserted. So the 3 million that were there and the 20 rows that were inserted during the distribution. And we can also now take a look at the data. I mentioned the Citus tables table. And we can see that now observations is present there. It's a distributed table on tenant ID. It weighs around 311 megabytes because the data we ingested was zipped. So when we pulled it over with the Azure Storage extension, the extension decompressed the data for us on the fly. And let's see how the data looks. We can imagine that even when you did that, some of your tenants might be not very comparable to others. You might have a big company loading a lot of data and a number of small customers that store a fraction of that. So let's look how our distribution looks like here. So by looking at the data itself, and grouping it by tenant ID, we can see that one tenant with ID 293 has significantly more records than all the other tenants present in the database. Now we will find the shard ID, the identifier of the shard that this specific tenant is assigned to, and this is shard 10.20.093. And now we can look at the shard sizes. So let's see how even the distribution is. And you can see we have a lot of shards, and one shard is standing out at 78 megabytes, and this is the shard 10.20.93, as we talked before. I can scroll up to show it. So we can see that's the same shard ID. So we know that this is taking significantly more data. It's skewing the data in into one shard. So how are they balanced per workers? The cluster I am demonstrating on has one coordinator node and two workers. So I can do this query to show for each node, for each table, what's the size of the shards assigned to this node. And we can see that the worker 1 is significantly larger than worker 0. So that's one situation where we, for example, would like to take this large tenant, assign him or assign this customer to its own shard, and move that to a new worker or rebalance it. Either way, isolate it from other customers because this specific customer has larger needs. So we can do this in Citus, and in Citus 11.1, this operation is non-blocking, like created table concurrently. So when we are doing this operation, we will again perform the inserts to the observations table while distributing the tenant to a new shard. So the distribution is now ongoing, and we are inserting new observations. So again, your application can continue to work, serve the business, while we are fixing the problem in our initial architecture, or we are reacting to changing requirements because businesses change and this client might have changed its usage patterns recently. So you were not able to anticipate that. Okay, so now the tenant is in a new shard and we have the shard ID provided to us. Let's reclaim some space so we can see more. And we can look again at how the shard sizes are. And this is the new shard, 10.21.10. And let's confirm that it matches with the one here. Yes. So we can see that this specific shard is now 74 megabytes. Now, nothing in the distribution itself changed between the worker nodes because we just moved the client to a new shard. We also would like to do something with the shard. So let's look at the balancing again. So we see there's no change here. And let's run the rebalancer. Before Citus 11.1, you had to maintain a pSQL connection to the cluster, run the rebalancer, and wait for it to finish. Now, with Citus 11.1, we introduce a new API and essentially a new framework of running jobs in the background that you can simply kick off, quit, and connect back to your cluster, and it still would finish. You don't have to keep this connection open. And as you can see, we have this new pgdisk background task and pgdisk this background job tables, which we can use to look at the running jobs. So let's look at the second job as we are suggested here by the hint. And we can see that, hey, we had job ID 2, task ID 2, started by Citus, it's done, and it did a shard placement. It moved one of the shards to another node, and we can look at the shard placements between the nodes. So we knew it was 69 megabytes on worker 0, 151 megabytes on worker 1. Now it's a bit more even. It's 73 megabytes on worker 0, 146 megabytes on worker 1. Now it won't be perfectly even because there's no way to move. The sizes of the shards doesn't allow a perfect split in this case. But if you added more nodes, the data could be more evenly spread out among the other nodes, or you can use some other Citus features to move the large tenant to its own node. And that's not the only thing we did with Trip Balancer. By having it run in the background, it's more reliable. It can restart on database recovery. It's faster. We spent a lot of time to improve its performance. And it's there to serve you as best as it can. And without anything more to add, thanks for watching my demo and have a great event.